A leaky 10 kilogram bucket is lifted from the ground to a height of 12 meters at a constant speed with a rope that weighs 0.8 kilograms per meter. Initially, the bucket contains 36 kilograms of water, but the water leaks at a constant rate and finishes draining as the bucket reaches the 12-meter level. The question is, how much work is done? And we're going to break this problem up into three components. So I'm going to let W1 equal the work required to move the cable, let W2 equal the work required to move the bucket, and let W3 equal the work required to move the water. And we're going to start off by finding W1 first. To find W1, let's place the origin at the bottom of the cable and the x-axis pointing upwards, so pointing in the positive direction. We're going to divide the cable into small parts of length delta x, and if x sub I star is a point in the ith subinterval, it's being lifted a distance of 12 minus x sub I star. The cable weighs 0.8 kilograms per meter. So the mass of the ith part of the cable is 0.8 delta x kilograms. Remember, kilograms is a unit of mass. And so now we're going to convert it to a force. The weight of the ith part of the cable is then 0.8 times 9.8 delta x, which is 7.84 delta x. So W1 is the limit as n goes to infinity of the summation from I equal 1 to n of essentially these force times distances. So in other words, it's the summation from I equal 1 to n of 7.84 times 12 minus x sub I star delta x. So again, W1 is the limit as n goes to infinity of 7.84 times 12 minus x sub I star delta x. If you can set up this Riemann sum, it's easier to transition from that into the integral. So the integral will then be from 0 to 12 of 7.84 times 12 minus x dx, right here. Okay? Now, I'm going to factor out a negative here. And when I do, I'll just write it right here. This is the integral from 0 to 12 of negative 7.84 times x minus 12 dx. Now, if I integrate that, we get the following. We get negative 7.84 times x minus 12 to the second over 2, evaluated from 0 to 12. And when I evaluate this, I get 7.84 times 144 over 2. And so therefore, W1 is equal to 564.48. And we're going to let W2 equal the work required to move the bucket. Oh, and before we do W2, before we find W2, the units for W1 is joules, which I'll call J. Okay. Now, let W2 equal the work required to move the bucket. So W2 is 10 kilograms. That's the weight of the, let me say the mass of the bucket, times 9.8 meters per second squared times 12 meters. And so W2 is 1,176 joules. Now for the fun part. We're going to look at W3. And reminding ourselves, W3 is the work required to move the water. It's very important to note that the water is leaking at a constant rate. And what we're going to do is we're going to let X be the amount of water in the bucket in kilograms, and let Y be the corresponding height of the water in meters. But it's very, very important to note that this water is leaked at a constant rate. Now, here's the question. How does X relate to Y? There is 36 kilograms of water at height 0 meters, and there is 0 kilograms of water at a height of 12 meters. As ordered pairs, we can write the ordered pairs 36, 0 and 0, 12. And there's a linear relationship between X and Y. So the slope is, in fact, 12 minus 0, right? Y2 minus Y1, essentially, divided by 0 minus 36, right? X2 minus X1, which is equal to negative 1/3. And so Y is negative 1/3 X plus 12. But we want to solve for X because X is in kilograms. That's a unit of mass. So Y minus 12 is equal to negative 1/3 X. So all I did there was just subtract 12 on both sides. Multiplying both sides by negative 3, we get X equals negative 3 times the quantity Y minus 12. And if I distribute, we can say X is 36 minus 3Y. Now, we can set up our integral essentially to find W3. So W3 is the integral from 0 to 12, and I'm going to take 36 minus 3y, and I'm going to multiply by 9.8 because that's going to convert it to a unit of force. And we're going to integrate this with respect to y. And that's going to be the work required to move the water. And when it's all said and done, W3 is 2,116.8 joules. Okay. Now, the total work required to move it all is going to be the following. My total work is 564.48 plus 1,176 plus 2,116.8, which is equal to 3,857.28, which is approximately 3,857 joules. And that'll do it for this video. This is a video on the leaky bucket example, and this is typically found in a Calculus 2 course in the section on work. Okay, thank you.